I'm Rohan Sarkar from Purdue University. I will be presenting our paper on learning dual pose-invariant category and object representations. Our goal is to learn pose-invariant representations for recognition and retrieval of objects both at the category level and at the finer object level. For this, we learn a dual embedding space to simultaneously learn category and object representations in separate embedding spaces. In the category space, we learn fundamental attributes common between different objects of the same category and that differentiates it from other categories. For example, all chairs have a seat and legs or a base and an additional backrest that objects from another category's tools do not have. In the object space, we learn additional object-specific attributes distinct to each object for distinguishing them from each other, such as different types of chairs with labels X, Y, and Z shown in the figure. Prior work focused primarily on learning category-specific embeddings with the object-to-object variations within each category captured within the same embedding space. Specifically, prior pose-invariant methods cluster single-view embeddings of an object close to its multi-view object embedding, which is then clustered close to the proxy embedding of its category. However, prior methods like PiCNN, PiProxy, and PiTC do not effectively separate the object embeddings as can be seen in the UMAP visualizations, and hence they do not perform well on object-level tasks. In contrast, our method decouples the two representations capturing category and object-specific discriminative features in separate embedding spaces. Also, unlike prior methods, we separate confusing instances of objects from the same category that would otherwise be much too close together in the embedding space. Since the embeddings are better clustered and separated, we learn more discriminative embeddings. For this, our framework PiRO learns pose-invariant representations of objects by comparing multi-view images of a pair of objects that are randomly sampled from the same category. For example, two different types of kettles in the figure shown. PiRO comprises a dual pose-invariant encoder that has a shared backbone followed by two separate heads for the object and the category embedding space. The encoder is trained using pose-invariant losses specifically designed for each space. In both the spaces, embeddings from different views are clustered to learn pose-invariant features. Further, in the category space, the embeddings of two objects from the same category are pulled close to each other to learn common features, while in the object space, the embeddings are pushed apart to learn discriminative features to distinguish between them simultaneously. Our dual encoder architecture is shown on the right, which takes as input different views of an object. The shared CNN backbone captures visual features common to both the category and the object representations, followed by two separate linear layers for each embedding space that outputs a set of single-view object and single-view category embeddings from each individual image. The single-view embeddings for each space are then input to a single-head self-attention layer that learns invariant features across different viewpoints, which are then aggregated using min pooling to learn a multi-view object and a multi-view category embedding. The attention map at the bottom shows the representative views of objects are assigned higher weightage. Now we explain the pose-invariant losses. In the object embedding space, we first find the confuser embeddings, which are the embeddings of different objects that have the minimum separation between them. The object loss has two components. The clustering loss pulls the confuser embedding close to its multi-view embedding of the corresponding object to learn pose-invariant features. The separation loss, on the other hand, pushes both the confuser embeddings and the multi-view embeddings of the pair of objects apart from each other to learn discriminative features to distinguish them. As can be seen in the UMAP visualization, the separation loss is crucial for learning discriminative object embeddings. In the category embedding space, we again have two losses. The clustering loss pulls the single-view embeddings of each object close to its multi-view embedding and additionally pulls the multi-view embeddings of two object classes from the same category together to learn common features between them. The separation loss is the L softmax loss that separates embeddings of different categories apart from each other. We evaluate our approach on three challenging multi-view object datasets, ModelNet 40, ObjectPy, and FG3D, on 8 pose-invariant classification and retrieval tasks, both at the category and the object level, from single or multiple views. The encoder is trained jointly using all the losses designed for the dual spaces. The table shows an ablation of the different losses in the single and the dual spaces. We can observe that the pose-invariant object loss improves performance significantly on object-level tasks as it separates out the embeddings of different objects. The effect is more noticeable in the dual space where the representations are disentangled and the losses can optimize the distances in the respective spaces simultaneously without conflicting each other, leading to overall performance improvements, especially for the object-level tasks. The results indicate that learning a dual embedding space improves performance on all tasks as compared to a single embedding space as highlighted in green in the table on all the three datasets. Specifically, we observed significant improvement in object-level tasks in the dual space as compared to the single space. This is because the inter-object distances are larger in the dual space as can be seen from the graph, leading to better clustering and separability in the dual space as can be seen in the UMAP visualization. Our method outperforms prior pose-invariant methods on ModelNet 40 and ObjectPy datasets shown in the top table and FG3D dataset in the table below. The most significant improvement is in the single-view object recognition and retrieval task as highlighted in green in the tables. This is because the object embeddings for our method are much better separated as compared to prior methods as validated by the UMAP visualizations. The single-view object retrieval results show that our method can accurately retrieve other views of the query object despite large variations in the object appearance due to pose changes. Our method also can accurately retrieve other views of the query object even when there are other visually similar objects in the dataset from the same category. Thank you very much for listening.